Repairing the NRU vessel is a technically challenging activity. Well, I've heard it described aptly by someone as trying to change the oil in your car from your living room. We're faced with conducting remote investigations in a radioactive environment with high radiation fields, conducting the examinations and inspections through small openings in the top of the reactor, and accessing over great distances, down 30 and 40 feet into the bottom of the reactor. So it's technically challenging. We're bringing together corrosion experts, material science experts, welding experts to look at repair options, as well as the remote examination combined with the overall safety and radiation protection that needs to be in place. We've got crews that are operating 24/7 in operations on non-destructive examination. We've got crews working through the night on equipment development and in engineering, doing 3D models of the reactor vessel so that we can simulate the difficult operation of entering the vessel and articulating in to conduct the remote repair. So this is a model of the NRU reactor. What we're interested in is the reactor vessel itself, which is this tank inside the reactor core. The vessel is about 3.5 meters in height and about the same diameter, so about 12 feet in diameter. The leak site that we're interested in is located at the bottom of the vessel, which is made from aluminum. In order to execute the repair, we're talking about introducing tooling from the upper deck plate here, down through narrow openings into the reactor vessel itself. The area that requires repair we've determined to be located at the bottom of the vessel in a region here. The problem we've determined is corrosion. Corrosion has been introduced from this annulus which surrounds the reactor vessel, and there's been corrosion into the backside of the aluminum vessel itself. So in order to repair the leak site, we have to introduce tooling down through these openings into the bottom of the vessel, and the tooling will deploy out to contact the inside surface of the vessel and execute the repair. The distance from the top of the reactor down to the leak site is about 9 meters, or roughly 30 feet, and all of the equipment and tooling needs to be introduced through these small openings in the top of the reactor and down through these channels, and the diameter there is about 10 centimeters, or in the range of 4 inches, 4.5 inches. So we're looking at multiple repair scenarios in order to bring the reactor back into service. It's technically challenging, but the repair methods that we're bringing to bear on this problem are all well developed and have been applied elsewhere. I'm very confident that we can bring to bear these technologies to repair the vessel at this leak site and any other locations that need to be remediated. At present, we've defueled and drained the reactor vessel, and we're partway through the extensive non-destructive examinations inside the vessel in order to characterize what needs to be repaired. Until we complete those evaluations and determine exactly the extent and the type of repair that will be applied, it's difficult to predict the time frame in which we can execute and return the vessel to service. Chalk River has a great technical depth in a lot of areas that are applied to the CANDU reactor industry, things like remote inspection, and we're applying that here to solve the NRU issue. Corrosion and material science. We have great depth in these areas, and we're bringing all that expertise to try and solve this problem. Radiation protection. We're bringing all of these disciplines to apply to this problem, and they're part of the strength of Chalk River as a national laboratory.